Hello, good afternoon. Myself is Karthee Sivalingam, and I'm going to present the work on analyzing monitoring data using LASSi for Archer, along with Harvey Richardson. We are part of the HPC and AI EMEA Research Lab. To introduce our lab is mainly involved with providing deep technical collaboration, working with customers on a long-term technical relationship, and we have wide research interest in memory hierarchy, data movement, compilers for optimizations, and also in AI and big data. We have engaged in different models with different customers based on center of excellence, on research projects, and also value add projects. These are the list of the current Horizon 2020 projects we are involved in: Expertise, Mastro, Epigram, Satellite. We work with a variety of university and industrial partners, and we also offer a PhD funded PhD students and internships in our team. As part of our lab, we have three center of excellence in EMEA. Uh, Archer is the UK's national supercomputer, and this work, LASSi, is based on the work done for Archer actually. We have two other machines, one at Coast and also GW4, which is the ARM collaboration, which is in Bristol. So I'm going to do it in three sections. I'm going to first introduce LASSi, and then probably also then show you the analysis we did on the LASSi data, and then move on to what are we doing next with the Metavis project. So we started developing LASSi mainly to gain better understanding of the performance issues in a shared file system. Why did we develop LASSi actually? This mainly started with the people, users of Archer reporting slowdown issues, and we took a lot of time to analyze why it happened actually. On Archer, actually, I think most applications are high performance computing application, and they use uh, compute memory and network and file system very well, but they all share the network and file system. And there are diverse workloads I'll show you in the next couple of slides. And sometimes they have runtime variations. And people report to these help desk that application runs slower than normal, sometimes not even able to do an ls on that command prompt. And these queries usually come to the help desk, and we need a way to identify why applications slow down or why something is happening, and whether this shared file system and network, is there a problem of contention there. We want to understand how the shared file system is used by different applications so that it will help HPC service providers to plan and procure, the project managers and admins to monitor and triage problems, and also at the application level for the developers and scientists to understand what type of IO they are doing, how they can develop their application, optimize their application, or use the HPC system in a optimal way. So we developed this LASSi, which combines the Lustre statistics obtained from a tool called LabCat, which was developed internally by one of our admin teams, and along with the scheduler data from the PBS in our case, we combine both of them and create an application IO profile. This application IO profile of all the applications running on Archer is then used to analyze runtime variations and how application runtime uh, gets impacted by contention. So in a Lustre file system, my job is running along with other jobs, and suddenly some rogue application comes in, and suddenly there is a runtime variation actually. How is my job running along with other jobs impact the runtime actually, and what is the risk of slowdown I can see? And also we studied what is the quality of IO and what its relationship to the IO job performance. So to understand this, actually, we came up with a novel approach based on risk. This novel approach is based on a simple philosophy. Like in isolation, a slowdown will happen only when an application does more I/O than expected, and users will report slowdown only when they encounter more I/O in the file system than expected. So this is the broad philosophy you're going to base that, and we're going to use this ideas to define a metric called risk actually. So this is the definition of risk. Uh, on a Lustre file system, we have both OSS and MDS. OSS refers to the reads and writes, and MDS to all the metadata operations. And our tool can collect stats for all these different operations. And for each operation, we defined a risk as the scale of deviation from alpha times the average on the file system. So this is calculated for each application run, and then we then calculate the overall risk to the file system at that time actually. So the higher the value of the risk, the higher the risk of slowdown. For example, for a particular operation, let's say uh, opens on a file system, there are two operations every a minute. Let's say an application comes in and does 12 operations per minute, then the risk is 5, considering alpha is 1. Similarly, for each of the operations on OSS, which are reads and writes, and MDS, which are opens, closes, which is the metadata server, we accumulate all these risks together as risk to OSS and risk to MDS, as shown here. Again, we also define one more metric to identify the quality of I/O an application does on a Lustre file system. On a Lustre file system, if you do 1 MB of read or write per operation, then it's considered to be very optimal. So we came up with this two metric, read KB ops and write KB ops, which denotes the read quality and write quality. This is similar to the risk in that a higher value of quality means it's low quality, or higher value of a read KB ops or write KB ops denote low quality, and a value of 0 or 1 denotes very good quality. Both these metrics, risk and quality, are defined in a similar way. The higher values are bad and lower values are good. This shows the architecture of how LASSi works. We have a LabCat tool which collects all the Lustre statistics. From the PBS, we collect all the scheduler data of the job data. And then this is then processed by the LASSi application and then ingested into a Spark database. Similarly, the scheduler data is filtered using a Python script, and then we do some extract, transform, load transformation on them, and then push it to a Spark database. LASSi uses Spark database as the main data analytics engine. And once all the data is pushed into this database, then we start analyzing this to identify risks and quality metrics of a particular application run. And then all this information is then pushed into daily reports and also to a safe application. Safe is the main front end where the users can submit their queries, and also where they can interact with the support staff of Archer. So this data is also sent to Safe, where the user can directly see their application IO, what they have been doing, and what are the risks and things like that. So this both these daily reports and safes are provided for the users to identify and understand their application IO profile. So with this, we have automated this workflow to provide a daily analysis. It's not a full real-time analysis, but we are moving towards it. We have a risk model which identifies slowdown in a shared file system. And then this has been also validated with our actual reported slowdown instance. We have been able to do this for the last couple of years. Of all the instances reported, we have been able to model them very well. I also developed an IO quality metric for studying the efficiency of application IO. This LASSi tool offers, along with this analysis, a coarse IO profile of each application running, an identification of abnormal file system and application usage, exact time at which it happens, and also exact application which are causing the slowdown. This shows an example of one of the daily reports which goes out. Here, x-axis is the hour. This is on a particular day in 2017. We had high risk, And on the x-axis, we have the risk to ASS. The Not only the risk to the file system is shown here, but also the top 10 application causing this risk is actually plotted on top of it. For example, at 5 o'clock, we had a restart application, a WARF application, and also a tracing application running at the same time. Each had a risk of close to 100, and then they all running at the same time caused a huge risk. Similarly, 3 applications running at the later part of the day, mid GC, MUV, running at the same time cause cumulative higher risk actually. Similarly, this is an example of risk to MTS on that day. This is even more interesting because these are task forms. I'm showing only the top 10 applications in the task form. These task forms are run hundreds and thousands of them at the same time. Even though each task has only little or very low risk, they are running all at the same time and they considerably increase the risk, actual total risk to the file system. As you can see, these things are very hard to identify without such analysis actually. Once we have this analysis from the daily report, then we go and say, what are the applications causing the risk? Why it's slowed down? And then we go and advise the users and also the developers on what are the things we can do actually. So this we have been doing for the last couple of years, and we have been very successful in working with developers to get their applications to tune, change their IO patterns. In the next section, I'm going to show you some analysis, a broad analysis we did on the data from April 2017 to November 2019. This is mainly to help the project managers and also the application owners to identify how they are using the Archer file system in general. So Archer has many projects. It's a file system which is used by, or HPC machine which is used by many consortia. These are the top 9 consortia which are one of the heavy users of Archer. Mesoscale engineering is looking at problems between microscales and macroscales. They use LAMPS and foam, mainly use lattice Boltzmann methods, mainly use them actually. And then turbulence simulations, used in naval, aeronautical, automotive, power generation, process, pharmaceutical, to name some. Combustion, uh, mainly around applications for computational fluid dynamics there. Then we have ocean science, looking at studying modeling the ocean, uh, famous application being NEMO there. Physics and cosmology involves n-body simulations, solar physics, particle simulations, looking at galaxy formations. Then geophysics and seismologies, looking at renewable energy, sustainable production of metals, uh, environmental impacts and risks, and again, uh, very important. Atomistic simulation looks at atomic scales in solid, liquids, and molecules and plasma, interaction with atoms and molecules, electron collisions, among others. Material chemistry, one of the most famous projects on Archer, which runs VASP, which is again a very famous application. A look at modeling and predicting structures, properties of materials. Strong emphasis on density functional theory techniques here. Last, we have the climate science, which is looking at modeling the whole atmosphere, modeling the whole Earth, and the MEROV unified model being one of the main applications there. So we want to learn how these projects are using the Archer, importantly the Archer file system actually. So this shows the pie chart of how these projects use the Archer actually. And on a broad scale, we can look at it, they read close to 59 petabytes and write 192 petabytes, which simply corresponds to 3 bytes written for every byte read. This is the general trend, but as we see, this trend changes. There's mainly 4 big projects, again, geophysics, atomistic simulation, material chemistry, and climate science, which have a huge chunk of reads and writes. And there's also a big chunk in the others, which shows the huge variety of applications running on Archer. Going to the next slide here, we look at 4 projects which don't follow the trend of reads and writes, mesoscale, turbulence, ocean science, and astrophysics. These applications don't write so much data compared to their reads. For example, mesoscale engineering, for every 4 bytes, it writes only 2 bytes of data. Again, ocean science has almost same amount of reads and writes, and astrophysics is uh, almost reverse the trends of writing and reading actually. Next, looking at the other 4 big projects which I mentioned, these projects follow the trend of the general archer, or they set the trend, you can say, of reading almost 1 byte and then writing more than 4 or 5 bytes of data for every byte read. Uh, Here, important the atomistic simulation in general writes almost 7 times for each byte read actually. So this is interesting. We can see two different kinds of projects going on in the Archer. Looking at the metadata load on Archer, this is the load on the different projects, how they use. We see uh, uh, that the ocean science, which was doing a lot more metadata, and material chemistry also using a lot more metadata than other projects actually. One general comment I would say is that the metadata load on a file system is more related to the reads on the file system. We expect the file system writes to be buffered, and they usually write to one or few files. So the metadata load is pretty low, whereas the reads, they usually write from multiple files, and the metadata load, which are the opens and closes, are more related to the reads. As you can see from at least the ocean science and climate science, uh, even though climate science does a lot more reads and writes, but the metadata load on ocean science is high compared to climate science. Um, we looked at the overall stats, but we need to look at trends actually. How, over the years, how these projects have changed over years. Maybe this will help us when we move to Archer 2, or when we move to Exascale. Here we are looking at a cumulative summation of reads and writes over the months in 2017 to 19. On the x-axis is the read and writes in petabytes. The most important thing here to look at is the slope. Uh, the higher the slope, which means these applications are ramping up their reads and writes. Uh, and there are 5 projects I have highlighted. These are 5 projects on the top, which are the big hitters. They read and write more data. And a lot of small 5 projects down here, which has comparatively very low reads and writes. Interestingly, we have this atomistic simulation, which is simply growing exponentially for the past year, actually, grown pretty fast. Whereas if you look at climate science, they have grown pretty gradually, but they have shown a pretty not much one not sorry they have not done much for the last year. So we can see such trends where they are going and predict where they might go in Archer 2. Actually, this might help us in the planning. Actually, this looks at the metadata operations. Again, this is very good to see that there are 2 applications: material chemistry and ocean science, just ahead of all the other projects. Uh, Again, we see huge trends of increases in ocean science, sorry, atmospheric science in general, and it's increasing uh, a lot in the last year, actually. So these are very interesting to see. From these trends, actually, I think usually Archer has multiple file systems. People can plan to have projects isolated across these file systems so that they don't have contentions among them. Then we looked at the projects in general. Let's look at the applications. Uh, these are the top 14 or 15 applications on Archer. Python, the code name Python refers to all code using Python. They are AI and big data application, which have started to grow in science in Archer. Archer doesn't have GPU, so there are not many AI codes still. Cast up and Elk or atomistic simulation codes, Atmos and GCME or climate science codes, BOF and Senga are codes for combustion, or WASP, AIMS and NWChem or material chemistry, LAMPS and foam for mesoscale engineering, XO is the IO server, which is famously used by ocean science. And for turbulence, we have Solver, Hydra, and Incompact 3D. So these are the famous applications. We have coded them. And we want to look at their IO using some scatter or bubble plots. So this plot shows us a scatter plot of the applications risk to OS and risk to MDS. Risk to OS on the x-axis, risk to MDS on the y-axis. Risk again denotes the quantity here, uh, how much more it does compared to the average. The size of the bubble actually shows you the actual number of jobs running. For example, we have VASP here. There are a huge number of jobs running, but the risk to the file system is pretty low, close to zero. We have applications like Solver, Sengan, Axum 3D. They do a lot of reads and writes, but they don't use the metadata server heavily. But a general trend is that a lot of applications use the metadata server heavily, but they don't do much reads and writes. A good example is Atmos, which has a lot of reads and write, but they do it very nicely with a low risk to OSS and almost no risk to MDS. An interesting thing is to see is the Foam and Python jobs having similar profile, and which is, and again, Lamps being one application which is doesn't have both a good risk profile on both OS and MDS. Uh, yeah. Let's look at the scatter plot of the read quality and the write quality of these applications. Read quality on the X and write on the Y. As you can see, only three applications stand out. Boffin, again, a higher value means bad quality of reads and write here. Boffin, which is very high number for write quality and read, just stands out. We've been working with this application user to make changes and make them better use of our system. Again, Sengan Hydra has a very bad read quality. In general, most of the applications have very bad read quality compared to write quality. As I mentioned, the write is usually buffered, and the quality is usually very good. Looking closer at it, actually, and we see the similar trend where reads quality is bad. Again, applications like CastUp, Ames, Incompact, GC, MUV have bad read quality compared to write. Uh, there are applications like Atmos, XOS, and ELK, which has very good quality of both read and write. One application which was also present at IC a couple of days back, Foam, they've been working on improving their IO performance, has very bad read as well as write quality. A long way to go there. So we looked at read and write qualities of the application and hope this will help the application owners to see where they are at and probably make changes to their applications so that they can use the file system a better way in Archer 2 or in other machines. We've been also looking at recently trying to port this LASSi to Office. I'll probably give an overview of what we are trying to achieve here. Um, so LASSi job profile. This is a profile of jobs and of Office jobs. As you see, they run a lot of jobs actually, close to 700,000 jobs or more than that every day. And we can see most of the jobs, the x-axis here on the plot, the x-axis is the number of jobs and the y-axis is the runtime in second. And most of the jobs runs less than a minute, less than 50 seconds. On Arch, this is not the case, as most of the jobs run for at least an hour. And this is a huge difference. Both the number of jobs and the profile of the jobs is completely different from Archer. As I said, and one more thing is that most proportion of the jobs actually use shared nodes, whereas this is not the case in Archer. So we have current mechanism to collect data for us for monitoring is LabCat, which collects at a 3-minute interval and usually doesn't collect data from shared nodes, actually. So this is not suitable for our mid-office integration. So we looked at Cray product called CrayView for cluster store, and we thought it's better suited for it. And we are looking at integrating LASSi with this monitoring data from CrayView. CrayView for cluster store will be extended as part of Shasta, which is our next offering, and it collects data over a fine resolution of 30 seconds. It has a lot more monitoring data other than Lustre. It also have network and other information and shows the information in a, you can view this information in a Grafana display actually. Just shows a overview of where the Crave view is. Crave view has a Lustre job starts. It stores them in a Kafka bus and then persists them in InfluxDB. So what we are trying to do is that push the data from InfluxDB to LASSi directly, and then come up with customized analysis as we are doing for Archer. So this is a project we are currently doing with MetaOffice. I think we'll present probably the results next year. Uh, I want to summarize here. I think LASSi provides an application-centric, non-invasive approach based on metrics to analyze slowdown. It has been very valuable in understanding the application I/O behavior in Archer. And with Archer 2, with a newer file system, we'll have more challenges and also more possibilities for changes, as you have seen. And also, we want to understand how does these I/O changes with object stores with still POSIX interface still there. We see different communities and applications stressing the file system in different ways, and the requirements of these projects or communities are changing rapidly in the last couple of years. And I think there is a need for working with project managers, scientists, developers at different levels to manage this IO requirements and demands. And I think monitoring and analysis is an important tool for us as we move towards exascale. And can we identify these rogue application behavior using machine learning? It's something we are very interested in. We are also looking at it, but there are a lot of challenges there. I want to end it there. I want to acknowledge our Archer, MetaOffice, and APCC have been helpful, and Epsec who funded us, and Craig. We are done. Thank you, and I can take any questions. Thank you.